Hello everyone, I'm here to present the paper The Woven Mind, Ada Lovelace, Intuitive Computing and Creative Machines. My name is Pei-Ying. I'm from Eindhoven University of Technology, and my co-author is Olaf Wikowski from Cross Labs. So in this paper, we are basically looking at weaving as a kind of computation, where the process of weaving is a computation with humans, yarns, and machines, and they work together as co-creative agents. We propose that we can look at textile as expressive and embodied systems. Our work is very much inspired by the poetical science, which is a term that came from Ada Lovelace. In her letter to her mother, Lady Byron, who was a mathematician, and where her father was a poet, she says that you will not concede me philosophical poetry. Invert the order, will you give me poetical philosophy, poetical science? And this really shows Ada Lovelace was looking at science that was considered something rational as a poetical thing, where she actually used her imagination in all different aspects of science. Ada Lovelace's perspective of seeing the rational science as a poetical thing expand her imagination to different aspects. So what you see here is the analytical engine. It was invented by Babbage right after he invented the difference engine. So the difference engine was mainly doing calculations, but the analytical engine was able to calculate functions. Ada Lovelace was translating an article that explains the analytical engine to the English-speaking crowd. But then, unlike a normal translator who translates word by word, she also wrote a long note on how the analytical engine is different from the difference engine. And she even made further interpretation on that and wrote the first program. So how she referred to the analytical engine was that she emphasized what makes it different is the introduction into it of the principle which Jacquard devised for regulating by means of punch cards, which in analytical engine it was used to control the analytical engine. So she said, analytical engine weaves algebraical patterns just as the Jacquard loom weaves flower and leaves. Well, so what does that mean? So first, let me explain what is a Jacquard loom. So here on the left hand side, you see a Jacquard loom, and you see the part that's being marked as the shaft and the header. So the shaft carries the header, and it lifts the header, where the header has the warp that goes through it. So when the header is lifted, the warp gets lifted, and then we throw a shuttle with yarns through the gap between the warp that's being lifted and the warps that wasn't lifted, which forms the weft. And then we move on to the next line. Some of the warp gets lowered and some of the warp gets lifted, and then we throw the weft again. Gradually, the warp and the weft are then interweaved into a fabric. So which warp gets lifted in a Jacquard machine is controlled by the punch card on the right hand side where you can see it. So the punch card decides which shaft gets lifted, so you can manage to create a pattern. So in Ada Lovelace's eye, by knowing how the Jacquard loom works, where she sees how the patterns are being controlled as a runtime operation through the punch card, she also sees that the punch card that controls the analytical engine are the runtime input of operations that controls the analytical engine. And where, following that thought, these punch cards can store mathematical processes that are being broken down to operations, numbers, and variables. And that was the basis of the early computer. She even made the first, or some of the first, computer programs in this chart, where she separates the function, the operation, and the variable. And nowadays, as you can see here, is a TC2 loom, which is controlled by pumps, where the pumps are controlled by the computer. We already replaced the punch card by the computer that allows us to do more sophisticated calculation. Now we can control each individual warp in this jacquard loom, and we replace the original machinery that reads the punch card. As many of you might already know, the weavers and textile designers actually use the loom to create the fabrics they want, where the fabrics are actually their expression of their sensorial emotions, the embodied knowledge, the texture that transmits certain expression. But then, as it's mechanically very close to the analytical engine, we propose that we can actually see the loom and the working, the making of the textile as a bridge between technical function and emotional expression, where we could perhaps see computation in the loom as a lifelike, creative, and effective way of computation. Therefore, we propose that we can see weaving as hybrid life. Before doing that, I would like to first explain what is happening in a weaving process. So in the weaving process, there's at least 4 interwoven layers. First, it was the pattern that controls and stores which warp needs to be lifted and lowered. So it's an abstract concept of the logic of the interlace, which later being interpreted as structure. The second layer is the yarn. Yarns have their physical properties, and like thickness, twist, elasticity, and it forms the final physical formation of the fabric. The machine, which is the loom, is the third layer. It takes in the pattern and mediates and enforces operations according to its mechanical constraint and affordance, but it also obey the instruction that's being given through the pattern. We also have human as the fourth layer, where the human, even in the industrial loom, will have to be standing there and looking at how the machine and the yarn performs and make design decisions or interventions to the machinery. All these 4 layers work tightly together, and it cannot be looked as a separate system. So it's a very hybrid, inseparable, complex system. What is essentially happening in the weaving process is an embodied translation that goes through the body material and machine synergy. So you see in the image, first is in the digital matrix that's being translated into a digital loom software, and then through the calligraphy of the machine forms the woven structure on the right. It's a little bit more sophisticated than this, but we can demonstrate the complexity of the system here. First, the abstract idea forms in the mind, and the weaver draws it down into the pattern. The pattern, and punch card sometimes, is then being fed to the loom, but also at the same time, the designer, the weaver, choose the yarns for the warp and the weft, and speculating how the physicality is going to unfold through weaving them together. In the third process, the machine performs the pattern. The weft shuttle is also performed by carrying the yarns and creating the weft. This is a status of a lot of movement. And once these movements are done, the warp and the weft are then woven together, which forms the textile. And if you take the textile off the loom, release the tension, then the textile forms its own texture because of the physical interaction between the structure and the yarns. Then, in this process, the designer, the weaver look at the textile and reflect on the texture of it through touch, through visual. They also evaluate the physicality of the textile by pulling it. And all of these embodied information then feeds back to the idea, where the weaver will change their idea, modify their idea, and then draw the pattern, feed it to the machine, create a new fabric. And this is highly complex. So in this process, it actually demonstrates a very important part that we see as an opportunity for artificial life, which is that textile has the ability of computation. What you see here is a waffle weave. It's created by a two-dimensional structure, but then it forms a 3D structure. How is it so? So you see the image on the left, which is the waffle. On the right is the pattern of the waffle. You see the square in black and white. There are big ones and the small ones. The small ones, because the yarns were interchanging quickly, so they serve as attachment points. The big square, meaning that there are yarns that goes loose for a longer distance, and that allows the yarn to express their physicality, which then in most of the cases the yarns will shrink a little bit, and that shrinkage pulls the fabric together, creating the three-dimensional structure that looks like a waffle. This demonstrates how the yarns can compute on top of the existing pattern. This is the work by Milu Forvinden, where she uses a highly twisted Japanese paper yarn that she got from the area of Kansai. That when you spray water to the paper yarn, it starts to twist or untwist, basically change form. So she used them to create the fabric. When the fabric is being put into the water, they change the shape. And this property is being used also in a more openly woven fabric, because it's open, so it allows the paper yarn to perform its physical property even more. So when being sprayed with water, you can see that it becomes more 3D, that it bends and becomes more thicker. Also, when it's being dried up, it becomes flat again. So in here, in this image, you can see how the yarns are performing individually on its own when sprayed with water. We also see textile as something that's able to hold memory. So in this example, which is a sample made by Femke Forselen, she acquires a cone of wool yarn, and then she uses another machine to over twist it. And this over twisting making the yarn always shrinks. So when she's weaving it, she allows the yarn to twist together using long floats. And when it's being taken off the loom, the float will shrink together, pulling the textile together. But if it's being applied by the hand with forces again, it will reform into a form that's similar to what it was on the loom. By seeing how the textile can be computational and can hold memory, we propose that we could potentially create a woven queen between the computer, the loom, and the fabric. So we could have the computer that either generates or creates the pattern that sends to the loom, where the loom then create the fabric by controlling the warp and the weft. The fabric being taken off the loom can become its own structural texture textile that is being then again read by the computer, that modify or recreates a new pattern that's being sent to the loom, made the fabric, and the fabric can be reinterpreted again and change the programming part of the computer. So by seeing all these like potential computational ability and the concepts, we think that the textile provides a very nice alternative thinking that we can look at for artificial life. So this is our presentation, and if you're interested, please look for this title so you can read the paper. Thank you.
Hello, everyone. Thank you for being here. And today I will present our paper, Can We Tell if ChatGPT is a Parasite? So this is a joint work with James Stowart, my colleague at Lancaster University, Leipzig. Our aim is to explore human-AI symbiosis through the lens of game theory and information theory. So why do we need to study human-AI symbiosis? Large language models like ChatGPT or DeepSeek are now everywhere, and people use them daily for different kind of tasks, ranging from learning, creativity to problem solving and other tasks. So this raises fundamental questions such as what is the true nature of this relationship? Are we heading towards to symbiosis where both human and AI can benefit mutually, or towards to dependency? So could ChatGPT even act as a parasite, basically meaning that gaining from us while weakening our independence? So biology tells us two different metaphors. Symbiosis basically means that mutual benefit, and parasitism means one benefits and the other weakens. Our curiosity is simple but powerful, I believe. Under what condition will humans stop learning from the environment and instead relying only on ChatGPT? Okay, so human-computer interaction is a very traditional research area in computer science. So for HCI research, they mainly focus on usability and the creativity of the users and how the technology can support it. But these studies are largely qualitative, and so they don't really capture the long-term dynamics and feedback loops between the human and AI and the environment. And the environment we consider as a very important element here. To address here, we propose a quantitative information theoretic model for human AI interaction. So our inspiration comes from the information theory of individuality by David Cocker and his colleagues. So they define an individual as a system that propagates its own states into the future. Using information theory, they measure when the system behaves as one individual. So we borrow this lens to ask, can human and AI merge into such individual? So here is our conceptual framework, which is quite simple. So at first, human works mainly with the environment, as we always do when solving a task. So we need this kind of environmental, also conceptual, in textual information to support us to make decisions. Over time, as the human queries the machine more and the machine learns more from the human's perspective of the environment, eventually the loop will tighten. The human will rely on the machine, and the machine feeds on the human's input. So at this stage, we can say that they're inseparable. And this basically they are functioning as one unit. So importantly, the human may lose the ability to interact efficiently with the environment, which is the hallmark that we're looking for in this parasitic relationship. Okay, so that's the model. Probably the only mathy part in this whole work. I'm not going to discuss it in depth, but we are modeling this three entity inside this whole paper using stochastic game theory model. So basically, we care about the environment and the user's state, and also the machine state. We define the environment state as whether the environment is noisy or not, the user state as the basic knowledge of the task, and the machine state as the fundamental model's state. It can be a good model or it can be a less good model. So we consider their interaction, and then we need to define the transition probability of the user and also the environment, also the machine. So we will have an immediate payoff of the user, and the user will produce a prompt to the machine based on their knowledge from the environment, and then observe the response from the machine. So in this way, the user is trying to balance the gain between the observation and also their cognitive cost while interpreting the observation and also interpreting the environment information. So using reinforcement learning, the user adapts its strategy to maximize the long-term payoff, and this structure allows us to study the condition of symbiosis versus parasitism. Okay, so from here, I will introduce the simulation part. We try to make the simulation as simple as possible. We implement this Q-learning algorithm with softmax action selection to simulate the whole stochastic game model that I just introduced. The transition probability are defined using logistic functions, and so we can tune the parameters inside the logistic function to characterize different relationship between the user and the machine. And also, we define the user, machine, and environmental state in a very simplified way. We just have binary state for all these three entities. And for the user, state 0 means the knowledge base is not so good towards to the task. If it's 1, then they probably have a better understanding. Machine state 0 means the fundamental model is not so great, and 1 means that it's great, it's fantastic. Environmental state 0 means the environment is stable, and 1 means that it's a bit random. We have a set of information theoretical metrics to evaluate the whole interaction, system entropy to capture the uncertainty or diverse the system state is, and mutual information to capture how strongly user and machines are aligned with each other. Transfer entropy will make us understand the direction of information flow, who learns from whom. There are two different scenarios that we focused on. The first one is the user-focused one. We basically ignore the randomness from the environment and only focus on the user and the machine. So for the first scenario, we have an unbiased knowledge. That basically means the user will have a healthy understanding towards the machine. It won't trust it even at the beginning very heavily, or it won't have any bias towards to it. So as we could see, we evaluate the system entropy. The user starts without any prior information. So at the beginning, the exploration is very high, the entropy starts very high. And then as the interaction goes on, we can see the user converges to effective prompts, and the entropy decreases. So the system become more predictable. And then for the biased information, the biased knowledge scenario, the user starts with wrong beliefs of the machine, and the entropy spikes as they struggle to unlearn it. And then it shows how early biases or the overly good initial response can surprise exploration. And that's caused the whole scenario, like the system entropy become flat for some cases. And then we can see for a higher reward, with the higher reward, the user quickly exploit the best strategy. So basically the user will trust the best fundamental model machine a bit better. And so as we can see, the system entropy collapses and the exploration stops. So this is dangerous and it's a bad relationship between the two, because early satisfaction can reduce a long-term learning. And the key takeaway here is entropy reveals the balance between exploration and exploitation. So too little exploration leads to premature reliance to the machine, which is a bad relationship that we don't want to encourage in most of the scenarios. And now we're trying to tune the transition probability inside the logistic function. So if we tune the machine weight omega m, then we are creating a more dependence from the user to the machine. And we can see the mutual information scenario. We can see that between them, they really increases and their state become more coupled together. We also tune omega S, which is the interaction strength. So strong interaction boosts the mutual information further. But if the environment is very noisy, so the omega E would be 3, then it can initially mask the machine's influence. And then we also have a look at whether it will adapt over time. Even in a very noisy environment, the user and the machine will still adapt over time, and then the mutual information recovers to a similar level. So this one is the second focus and second scenario of the whole work. And we have the user AI environmental scenario. There are 4 different cases we're discussing about. So the first one, high coupling user and AI. So the AI will have a stronger influence on the user. And then we have the low coupling one. There is a weak dependency between the user, machine, and the environment. We have high coupling with impactful environment, means that they're highly coupled, but the environment is also very random and diverse. And then we also have high coupled with stable machine. The machine strongly influence the user, but changes very slowly. As we could observe from the figure, initial spike, the system entropy jumps as the system diversifies from a fixed starting state into multiple different possible trajectories. Some key information here is low coupling produced the highest entropy, so the orange dashed line on top. And this transition is more random and generating more overall information. And then we could see the high coupled with stable machine, the red line on the bottom, the entropy stays very low. So the machine is less sensitive. And then we have some cases in the middle. So what I want to highlight is that with a higher diverse environment, it is generally a little bit higher compared to generic case with the high coupling case. So, and then we have the mutual information. So the mutual information is slightly with the same trend with all different 4 cases. So it reveals how tightly the user and machine's stars are very aligned, and then a stable machine produces strong alignment. And also, while the environmental variability disrupts it and encourage exploration. So eventually it's settled down in the same level. This is perhaps the most important finding in this pilot study. We have examined the user entropy, machine entropy, and also the mutual information inside one figure on the left-hand side. So we could see the user remains in a very diverse state, and the machine entropy decreases a little bit, and because the machine compresses information and then become more deterministic over time. The mutual information first spikes when both of the user and the machine are listening to each other, and then it drops. So For the transfer entropy part, we can actually see the direction of where the information is transferring, and it is very asymmetric. So the user to machine influence is very strong, but the machine to user influence is minimum. And that actually proves that there can be parasitic dynamics between the two. So the next step, we're going to conduct a user study to calibrate the model, mainly the transition probabilities inside the model. We're going to study a more conceptual model in the large-scale human AI interaction ecosystems, and then try to reward design for symbiosis, but not parasitism, unhealthy relationship between the two. So some highlight of this work, we bring game theory, information theory into human AI interaction, shows that a ChatGPT can be parasitic. And also, we want to provide a tool set to design better, healthier, and more balanced human AI relationship. That's it. Thank you very much for your attention, and please reach out to us if you have any questions.